Today, my plan is to briefly review what I talked about in lab last week, and then I'm going to hopefully finish introducing all the RISC-V assembly language stuff. And then part of that is I'll show you some demos, we'll run some code, and then I'm going to switch topics a bit and talk about something called fixed point representation. Have any of you heard of that? Use that in 313 at all? They used to. But we'll talk about that, and then I'll introduce Lab 1. So if you go to Dropbox, it should be updated now. I've got the syllabus, the lecture recordings on there. Under important links, there's a thing called JRE download to run RARS. So we use a simulator, a RISC-V simulator called RARS. It runs in Java, so you need a Java virtual machine. So I got a link there if you want to run that on your own system. Then we've got some other miscellaneous downloads. We've got RARS itself. RARS is on a GitHub repo, but we've got a modified version that allows you to do I/O with the FPGA boards, and I'll talk more about that soon. But you can download that there, or you can use it on the lab machines. Lab 1 is where you use RARS to basically write some code. It's the only lab where you don't need the FPGA boards in the lab. So you could do Lab 1 on your own system if you want to. Lecture slides are under downloads. I've got the first lab already posted. So I mentioned when I was talking about the syllabus that late penalties only accrue during school days. So I used to have the labs due on Friday, and then the obvious question was, if it's due on Friday, but late penalties only accrue on school days, then you don't really lose anything by turning it on Sunday. So I ended up just changing the due dates to Sunday, right? Just to make that more clear. So if you think it's weird for it to be due on Sunday, that's the reason why. So it's due on September 6th, which is a Sunday before midnight. And then there's some links here to the RISC ISA. I've got the official version, and there's a reference card from the textbook. And then I think there's some example RISC-V programs on there. So let me know if you have any issues with Blackboard. Okay, so last time I just introduced the lecture, and then I talked about why we're covering this assembly language stuff. So there's instruction set architecture and microarchitecture. The goal of this course is to learn how to design microarchitectures, but in order to do that, you have to understand the architecture part, which sits on top of the microarchitecture. You guys with me? So you have to understand assembly language in order to design a circuit that runs assembly language, basically. So I try to minimize the time we spend on that, and I realize that some of you may have forgotten the assembly language part of 212, and others of you may remember it really well, in which case you're going to be really bored by this lecture. But I'll try to get through it fast. But if you have any questions, some stuff I'll kind of blow through. So if there's anything confusing, feel free to stop me. Okay. Right. So I talked about one of the yes. What software that we need? So it's called so there's lots of RISC-V simulators out there. There's a whole bunch of them now. You can actually, they have some that actually run on a website and stuff. But the one that we use is called RARS, RARS, and I'll actually run it today and show you how it works. It's a little dated now. It's a Java app, and they wrote it as a Java app so you could run on Linux, Mac OS, and Windows, but you need the Java virtual machine to do that. And you don't have to use that one. You can use another one if you want. There's probably better ones out there now. RISC is really kind of a hot thing right now, so there's a whole lot of simulators out there. Okay, so one of the things about RISC architectures that I mentioned is kind of an annoyance, as if you're trying to write code for it, is they use this load store architecture where you always have to bring data into registers somehow. You manipulate the data in the registers, and then ultimately you have to store it back to memory. Alternatively, you may not get the original value from registers. Like in this class, we're actually going to get the original input data from an I/O device, from the switches on the FPGA board. And then instead of writing it back to memory, we're going to write it onto the hex displays on the FPGA board. But the principle is the same. You pull data in from off-chip into the registers. You number crunch the data in the registers, and then you send it back out, which introduces this notion of having to remember what registers are being used for what, and also remembering which registers are live in your codes so you can avoid recycling registers too early and introducing bugs in your code. The other thing I mentioned last time, and I did not describe this very well, at least in the Wednesday lecture. I think I did a better job in Friday. But in in RISC-V, just like in MIPS, the registers are just the physical registers are numbered 0 to 31, and so they're called X0 to X31 in your code. But you can also refer to them in your code as alternative symbolic names, right? And this introduces some confusion because you can either use the X version of the registers in your code, or you can use the symbolic versions. The reason why there's symbolic versions is that there are some coding conventions at work here. Bless you. So there's 12 registers. There's a set of 12 registers, S0 to S11, which are supposed to be saved across subroutine calls by convention. It's not enforced, but you're supposed to do that. We're not going to be writing any subroutines. Well, you can if you want. If you want to, you can. But we're not going to do that. We're not going to go into that kind of depth with the coding. We're basically not doing subroutines, so the notion of registers being saved is not important in this course. But they still have these alternative names. Then there's T0 through T6 that are temporary. They're not saved across subroutine calls by convention. A0 to A7 are arguments for functions. And then there's the return address, stack pointer, global pointer, and temporary pointer, which by convention are pointers to that space, right? And then there's the 0 register, which is register 0, which always is read as the value 0. You can write to it, but if you read back from it, it's always going to come back as 0, okay? Now my whole thing would be like, just use the X registers. Don't use these, right? The problem is that sometimes you have to, because when you use the system calls in the simulator, they actually they refer to these names, like they use A7 to denote which system call you want to call. So sometimes you end up mixing them together, but I'll show you examples of that here in a minute. Okay, so this is the map. I didn't have this last week. I added this just to make it clear. So register 0 is 0, register X1 is RA. So in other words, you can either say RA in your code, or you can put X1 in your code, but they both refer to the same register, right? You can also mix and match, but keep in mind that if you write to RA and then you read from register 1, you'll be reading whatever you wrote to RA. You guys with me? So they're interchangeable. But the mapping is kind of weird. This is why I don't have it memorized, because like X5 to X7 is the first three temporary registers. X8 to X9 are the first 2 saved registers. And then the other save registers start at X18. I mean, this makes no sense. I don't know where they came up with this mapping. It's completely nonsensical. The other thing that you might have noticed is this return address is actually one thing that is implemented in the hardware. Return address is when you call a subroutine, this not automatically, but by default gets written as the return address. It's the link address. You might remember from 212 that was also in MIPS, but it was register 31 in that case. You guys with me? Okay, yes? Yes, yeah, I added it earlier. I'll update the slides online. Sorry about that. Yeah, I usually end up tweaking the slides right up until I give the lecture, so sometimes the ones online are a little out of date. Okay, so I mentioned register 0 is always 0, so sometimes you can use this to, for example, if you write this line of code where you're adding the contents of S1, see again, I'm using the symbolic ones here, because I got these from, I think these slides came from the textbook, that's why. So if I add S1 to register 0 and put the result into T2, this effectively is just copying the contents of S1 into T2, right? So this is a copy. Sometimes you want to copy contents of one register to another. There is a move instruction that you can use, but it's actually a pseudo instruction that gets translated as this, right? And add to 0. You guys with me? If I'm going too fast, please feel free to ask me to slow down. I mentioned last time too that some instructions have immediate values, and immediate is a constant that's baked into the software and cannot be changed at runtime. So unless you have self-modifying code or something. But for all practical purposes, if you have an add immediate, for instance, and you're adding 4, you can't change that 4. It's locked into the software kind of permanently, right? So this is for adding a constant 4 to the contents of register 3 and putting the results into register 3. So this is an increment by 4, right? So in this case, basically we have 2 registers in the instruction instead of 3, right? 2 registers plus an immediate. So the 3 register version of this, the add with 3 registers, is an R-type instruction. And the version with one register and an immediate is an I-type instruction. So these 2 types of instructions are encoded differently. And I'll review that too. You might remember that from 212 though. Sometimes you run into some weird oddities. Like for example, RISC obnoxiously does not have a subtract immediate. It has a subtract instruction with 2 registers, but it does not have a subtract immediate instruction where you have 1 register and a constant. Instead, you have to use an add immediate with a negative immediate. Now, you might say, how am I going to remember that? Well, you'll know because you'll get an error. Like when you type in, like if you type in subtract sub I, subtract immediate, you'll get an error. It'll say, that's not an instruction. And you're like, how can that not be an instruction? I thought there was an immediate version of all the non-immediate instructions, but there's not, right? So sometimes they'll require you to do stuff like that. But this is something that you'd only know this through trial and error or by reading the like the reference card. Okay, and then let's see. So backing up here a little bit, I mentioned that in the old days with the so-called CISC instruction sets, you could refer to memory locations in the instructions themselves. You can refer to memory addresses in there, but that's no longer the case. So now with RISC or any kind of load store architecture, you have to load your registers, memory locations, variables. Load your variables into registers, do something to them, and then store the result back, right? So what this does is this creates a lifetime for the registers, because by loading a register from memory, you're initializing it, and then when you use it, you're using it. And so the register becomes alive when you initialize it, and it's kind of dies the last time you use it as an input, right? So this kind of creates this notion of register lifetimes, right? But it also requires that you as a programmer have to remember, what variable is in which register, which is, I think, the hardest part of assembly language programming. Okay, so this is a new slide too. So this was the bug I showed you last time. So this time I thought it would be cool to actually look at this lifetime idea. So this is a sub-expression, just an arithmetic expression that has, it has 4 terms, but only 3 variables, right? B, C, and D, right? 3 input variables, and then of course A is the output, right? So what's happening here is when you load B into T0, T0 becomes alive at that point, and then the last time you use it is when you add this B, right? Because of the order of operations, pretty much the last thing you have to do is add that B, right? Because it's, it's the last operation that's done mathematically, right? So that's the lifetime. It's born here and it dies here, right? And then likewise, T1 is born here when you initialize it, and it actually dies in the very next instruction. So you load C, you use it once when you add it to B, and then you're done. It's gone, right? So it's only that register T1 is available for reuse in this line as soon as this line of code. You just don't want to, it's basically only alive for 2 instructions, right? And then likewise, T1 is actually recycled down here. So T1 is used again. In this case, instead of loading to it, I add and put the result into T1. This is where it's born, it's initialized, and then I store it back to memory. Here is where I'm done with it. So T1 does get reused. It gets reused twice. It's alive in 2 different periods of time for 2 different purposes, right? In this case, it's holding C, and in this case, it's holding the final value of the expression, right? So 2 different purposes, but recycling the same register. And then T3 is initialized here when we load, sorry. All right, did I screw that up? Sorry, T2, yeah, sorry, T2, I got ahead of myself. So T2 is also initialized here, and it's used to hold B plus C. So this sub-expression B plus C is put into a temporary register T2, so it's born there, and then it gets consumed when I multiply D. When I multiply it with D, then I'm done, right? And then finally, T3 is initialized here when I load D into it, and it's pretty much used up in the very next instruction when I multiply it, right? Yeah, when I multiply it, right? So I load D, I multiply it against the temporary variable, and I'm done, right? So the bug in this code, if you remember from last week, was this guy here. T0, I attempted to reinitialize T0 in this multiply, right, as a temporary variable. But what I didn't realize when I wrote this is that it was still alive it was still holding B, and I still needed it for B, right? So it was still alive, and I tried to recycle it so that blew away B, and so when I tried to re-add B at the end, it would have added the wrong value, so that's the bug in the code, right? So just watch out for stuff like that. Okay, so I also mentioned if conditions, and assembly language has these things called branches. Branches test a condition, which can be equal, not equal, greater than equal, less than or equal, right? And then there's, I believe there's unsigned versions of those too in RISC-V. Yes, MIPS was the one that didn't have the unsigned versions. That's one of the differences. So essentially, you're comparing the numerical value of two values, and if the comparison ends up true, you jump elsewhere in your code. The problem is that if you're writing high-level code, that's not how it works. If you have an if statement and the condition is true, you just drop down and do whatever's under the if, right? So the way I do this, and this isn't the only solution, but the way I do it is I just negate the condition. So I want to say, instead of if A of, the original condition is if A is less than B. So in order to maintain the same ordering of the code, whereas the if is the first part and the else is the second part, I just test the complement. I say if A is greater than or equal to B, right, which is not less than B, right? In other words, it's just the logical negation, at which point I go to the else part, right? You'll notice there's an else label here. And then if the condition is false, it means the original condition was true. So I just basically don't take the branch. I go through what they call the fall through instruction, which is the instruction after the branch, meaning the branch effectively didn't have any impact on the control flow because the condition was false, right? So it fell through, at which point I do the if part, and then I unconditionally branch to exit, right? Skipping over the else part, right? So the problem is, you know, once you do this a few times and you get good at it, it's not a big deal, right? But the first time you see this, it's confusing because it just doesn't match up to the same constructs that you have in normal structured programming languages, right? Yeah, so I have the graphics here that show this is the condition. The condition is represented by the branch. The true part is here, where I basically set a constant 1 to T0 and store that to A, and then I bail out. And then the else part is I store a 2 to B, and then I fall through to exit. Okay, does that make sense? Everyone clear on that? Is this too easy? You guys all remember this still from 212? Yes? Yeah, so the first thing you have to remember is that S1 and S2 are representing A and B, right? So you first have to, you have to look at the loads to establish the correspondence between the original variables in the C code and the registers. Okay, so first you have to remember S2 is A, S2 is B, right? Then we're checking to see if S1 is greater than or equal to S2, meaning if A is greater than or equal to B, right? And the reason I'm harping on this is because that is the opposite condition that I had in the original code, right? So what I'm doing is I'm trying to translate this high-level code to assembly. I'm acting as the compiler, right? I'm pretending I'm the compiler here, right? Does that make sense? And so now you might say, well, come on, man, why don't you just put the else part first and the if part second? Like, what's your problem with that? Well, I don't. You could do it that way too. That's fine, right? My point is there's more than one way to generate this code. But my point is I want to have the if part first and the else part second, right? Because I'm weird about that. But you could swap these in the code and then not have to negate the condition, right? There's more than one way to do it. Or you can add some extra instructions to keep the condition consistent and still have the if part first, but it's going to require more instructions. Okay. All right, and then finally, last thing, I think this is where I ended up the last lecture. Arrays. Arrays are a real problem in assembly. Real big problem. Part of the issue with arrays is if you write a for loop like this, where you have I, right? And use I to control how many iterations of the loop you go through. So in this case, 100 iterations. But I also use I as an index to this array. That's a problem in assembly because you can't really use your loop iterator variable to be your index. It just doesn't work out that way, right? So what you end up having to do usually, unless you come up with a trick, some kind of way to work around this, is you end up having to maintain a separate counter versus your address. So in this case, I'm loading x0 into x1. Why? Well, because that's I, right? So I'm initializing I to 0, so x1 is I. And notice I increment x1 by 1 at the end of my loop. And I also check x1 to see if I should continue looping, right? So x1 is my I. It's my initialization to 0, it's my add to 1, and it's my continuance condition, right? However, vals is a separate thing. So vals, I load the address of val into x2, and x2 I increment separately by 4. Why by 4? Because it's declared as an integer array, and integers are 4 bytes, right? And this index register x2 has to be byte addressed, right? Everything's in bytes because there's no compiler to do the type conversions for you. So as someone who's writing this code, I know it's an array of bytes, and therefore I should be walking by 4 bytes as I iterate. So my point is that x1 is I and x2 is my kind of my address, the thing that's incrementing the address, right? They can't be the same. Okay, that's annoying. Yes?
You don't have to negate the less than condition?
No, that's a great question. So yeah, in this case, that's a great question. In this case, it's a little different than an if statement because this is a continuance condition, right? So the way this is structured is if I is less than 100, I want to do another loop, right? So it works out a little better this way because you just check to see if x1 is less than x4. x1 is obviously I, x4 is 100, right? And so I can directly just check to see if I is less than 100, and then when I take the loop, it means keep going, right? So because the loop construct is fundamentally different than an if, it actually maps better to assembly language. But I'm glad you asked that. Yeah, I was actually thinking that when I was going over these slides today, that is a contradiction. Like if statements are weirder than it actually, like I said, it works out better with loops. Okay, all right, so here is, there's a lot of instructions, and I try to come up with a way to make this a little bit more interesting than just rattling these off. So I have put together, as I mentioned, if you look at the RISC-V instruction set, I think there's like 40 instructions in the base instruction set and 8 in the multiply. There's about 50 if you want to do base plus multiply. In this class, we're only doing, 20, right? So I'm actually going to list all the instructions that we will implement by the end of the semester, and I'm just going to look at those because it's not technically all the ones you should have if you're building a real RISC processor that you're shipping out. And you might say, well, what's the risk there? Well, the risk is that if you don't have all the instructions that are part of those instruction sets, then someone's compiler may generate an unsupported instruction, right? So that's the risk. But we're not worried about that. Since we're writing assembly, we're not using the compiler. So we're just going to create a set of instructions that'll give us, Turing completeness, so we can pretty much run the programs we want to run on it, right? Okay, so here's our first batch. These ones are grouped together because these are all 3 register instructions. So 2 operand, 1 destination, and they're all number crunching instructions, which means arithmetic, logical shift, and comparison, right? They're all very similar, and in the hardware, they all do exactly the same data path operations in the hardware. The only difference is what the ALU does, right? So these are all identical hardware-wise except for whatever the ALU function is, right? So we have, this is a complete list. These are all the ones we're going to put in. We have add, shift left logical, shift set less than. Yeah, it's easy to get those confused. Shift left logical, SLL. SLT is set on less than. Then there's set on less than unsigned, and multiply H, and I have another multiply h. That should be multiply hu because these are unsigned. Yeah, sorry, that's a typo. Let me fix that. Mul hu. And, oh yeah, and actually, sorry, this is not a complete list. I have the complete list. Sorry, I have the complete list here. So it's more or less the complete list. The difference is there's a couple other shift instructions too. There's shift right arithmetic and shift right logical, right? So I think it's all of them except for those two. Okay, you guys with me? Make sense? Okay, so I have Mars here, and this is going to be a little difficult to read. So I'm going to zoom in a bit. Okay, so this, oh, hold on, let me zoom back out first. So this is RARS. Mars was for MIPS, RARS was for RISC-V. So it's this Java program. It's kind of cool. It has an editor that's built in, and it has a simulator and a debugger. Probably there's a VS Code extension that does all this. I should have checked that. I'm sure there is. VS Code can do everything now. But you might even be able to use VS Code to do all this stuff. But this is RARS. And so these are the instructions that I just showed you on the slide. I just pasted them in. Notice the comment is, these are comments, right? And it does syntax highlighting. This is the registers. You can see the registers are shown here, both with their symbolic representation and their numeric representation. And then it shows you their contents in hex. You'll also notice that, well, it's not shown there. Hold on. If I scroll up, you'll notice that the stack pointer and the global pointer already have stuff in them because there is a stack and there's a global variable space. I'm going to just end up overriding those, blowing those away. I'm not using the stack, okay? And you might say, well, why not just avoid those ones? Well, because they put it at 2 and 3. I want to use the lower numbers, right? Okay, so if you want to run this, you just hit the assemble button, and let's see, let's change this a bit. Okay, so when you hit assemble, and I'm going to zoom, yeah, there we go. So when you hit assemble, you can see that there's an address, the corresponding machine code instruction. This is the real instruction, and this is the one that's in your code. The difference is sometimes instructions in your code are pseudo instructions, so they get, like I told you, the move instruction is an example, right? When you move a value from one register to another, it just becomes an add to register 0. So sometimes whatever you type doesn't exactly match to what gets put on the machine, but you see that difference here. You guys with me? Okay, so then let's see, if I want to simulate this. Oh, one other thing too, if you go to settings, I want to, values displayed in hex, I want to turn that off. I want to see the values in decimal for now. And so I'm going to initialize, if you look at the code here, the first thing I do is add registers 2 and 3, but I didn't initialize those anywhere. They're not initialized. So I'm going to have to initialize them in the simulator. So I'll go back to the simulator and just put some values in for 2 and 3. So I'll just put in, I'm going to type in 2 and I'm going to type in 3. Okay, then I'll come back over here. And if you hit this button, you'll notice that this guy is highlighted, meaning that that's where the program counter is pointed, and meaning that that's the next instruction that will be executed. This simulator does not simulate pipelining. It assumes that each instruction is executed atomically, right? Some simulators will, it'll actually show you which instruction is in which stage of the pipeline, which actually would be useful for this class because we are going to build a pipeline CPU. But unfortunately, this one doesn't do that. So there's just one current instruction, right? And when you hit next, executes the whole instruction, right? Okay, so in other words, what I'm trying to say is the next is not equivalent to a clock cycle, a clock tick, right? Okay, this is more of just an instruction debugger. Okay, so what's going to happen? Well, I mean, obviously, I forgot what I put in there already. I put 2 and 3, right? So it's going to add 2 and 3, which is 5, and x1 should become 5, right? So I'm going to hit next, and there it goes, 5. And it also, it helpfully, highlights the changes there. So then I'm going to shift I'm going to take x2, which is 2, and I'm going to shift it left by 3 bits, right? I'm going to take 2 and shift it by 3. What's that going to do? You guys remember?
It's multiplying by 8.
Exactly. Yeah, it's going to multiply by 2 to the 3rd power. So it should put 8 into x1. Let's see if that happens. Oh, no, it put 16. Oh, because it multiplied, the original value was, wait, hold on. I can go back. Check this out. You can go back, right? So there was 5. So there was 5. 5 should have been multiplied by 8, right? Oh, interesting. Oh, yeah, but it didn't, no, it's just overwriting 5. It doesn't use 5 as an input, right? It's using 2 as an input, right? So 2 is 2, and it's going to multiply 2 by 8, right, which is 16, right? So 5, it just doesn't get used at all, right? 5 gets set, but it never gets, it's kind of a, this is a test program. Normally 5 would be used for something, which is why I was confused. Right, so anyway, hit next, now we have 16. All right, set less than. So this is the one you guys might not remember. Set less than is checking 2 and 3, which again is 2 and 3. It's going to check if 2 is less than 3, right? And if it is, it's going to put a 1 in the destination register, otherwise 0. So it should overwrite that 16 and just become 1. There it is. Set less than unsigned does the same thing, except it does it with unsigned arithmetic, but since both values were positive anyway, the sign bit on both those 2 and 3 were 0, so it's not going to make any difference. And then we do an AND. So this is a bitwise AND. Bitwise AND of 2 and 3. So 2 in binary is 1, 0. 3 in binary is 1, 1. So if you do a bitwise AND of 1, 0 with 1, 1, you should get what? You guys remember that? So if you have, there's 2 and 3, and I'm doing an AND, right? So it's a bitwise AND, so it's looking bit by bit, right? So 1 and 0 and 1 is 0, and 1 and 1 is 1, right? So I should get a 2. Should get a 2 there. There it is, 2. Then I have a multiply, so 2 times 3, 6, so it should get a 6 in there. There it is. Multiply H. What's that do? Multiply H is going to multiply the values, but when you multiply two 32-bit values, you really get a 64-bit result. The first multiply only stored the lower 32 bits of that result, right, in the register. This one is going to store the upper 32 bits, which in this case is 0, right? Because when I multiply 2 times 3, the upper 32 bits of the product were of course 0 because the numbers weren't big enough to put any 1s in that upper 32 bits. So I should get a 0 there. And then there's another mul h, which should have been mul hu. And then add I. Did I put an add I? I didn't have an add I in there. Where'd that come from? No, I don't know where that one came from. There should be no add. I don't know why there's an add I. But anyway, the last, it was a multiply HU. It should have been the last one. Okay, any questions about that? Yes?
Does RISC-V have a high-lower register for...
No, and I'll talk about that more, but there's actually 2 instructions. So to recover all 64 bits of the product, you actually have to have it execute 2 separate instructions, mul and mul HU, or mul H, if it's signed, right? So in MIPS, yeah, there was a high and low register, but RISC, they said that the guys that came up with RISC were the same guys that came up with MIPS, but they evidently regretted that decision to do high and low, so they reverted that. Okay, so next we have some immediates. Right, so there's the add I. So I thought I had that in. Oh, I know what happened. It concatenated those. Interesting. Okay, I see what happened. So if we go back to edit and we go to RISC-2, RISC-2.asm, there's the add I. I think what it did is before I came in here, I did a thing where I told it to assemble. I told it to assemble. Yeah, I did this. I said assemble all open files. Yeah, assemble all open files. But anyway, it concatenated them together. That's not a big deal. Okay, anyway, so here we go. This is, where's my stuff? Okay, well, yeah, it did, wow, it did do that. Okay, well, that's fine. So can I just assemble this one now? Huh. Yes, that's a setting. You're right. Assemble all files currently open. Thank you. That is the way to do it. So if we go back here and hit assemble, it should just, yeah, there we go. Perfect. Thank you. I didn't realize that was a toggle. Okay, cool. So now we have, can I resize this or no? No. No. Okay, I'll just have to, that's fine. Okay, so back to, that's the data segment. Where's my code? Code. Text segment. Here we go. There we go. Okay, cool. So let's initialize x2 again because it got reverted. Let's put 10 in, let's put 2 in there. And yeah, that's all I need. Okay, so I'm going to add 10 to 2. So there's 12. There's 12. I'm going to add 10 to 2. Is it the same instruction? Yeah, I guess so. And then I'm going to shift. So this is a shift left logical immediate. This is going to take whatever's in 2, which is 2, and it's going to shift it by 10 bits as an immediate, which means it's going to multiply it by 2 to the 10th power. So it's going to become 2 times 1024, which is 2048, right? That's what we should get in there, right? And there it is, 2048. If you got, can you guys read that? Can you see that? 2048. All right. All right, so that's the immediate instructions. And then we have got branch and jump. So these ones are a little harder to debug. So if we go back to there, go to edit, go to RISC-V. Okay, so this one, what I've got here is a mixture of stuff. So I've got a branch less than. If x1 is less than x2, I'm going to go to skip, right? So I'm going to initialize those with 1 and 2 again. And since 1 is less than 2, it'll take the branch, it'll go to skip, and then I'm going to jump and link to reset. So it's going to go back to here. But because it's a jump and link, it's going to store the link address because I specified a register. It's going to put it in x3. If I hadn't put anything here, it would use x1, you know, the return address by default. But it's going to put the link address into x3. Does anyone know what that means? That means it's going to write like jump, you know, when you think of jump and link or jump instructions in branch, you don't think of them writing a register, right? That's usually arithmetic instructions, write registers. But in this case, it's actually going to write register 3, but instead of doing some kind of ALU operation, it's just going to take the program counter, which would be pointing at the next instruction, this no op, and it's going to put that into x3. Basically, it provides a return address, like as if this was a subroutine call, right? So I'm going to jump to reset, at which point I'm going to add x0 and x2 and put the result into x1. And then I'm going to jump register to x3, which is then going to jump down to this no op because that was what's in x3. You guys with me? So it's kind of a complicated sequence. I'm going to do this instruction. Then it should go to this instruction, then this one, then this one, then this one. So it's going to be bouncing all over the place if I did it right here. All right, let's see. Let's assemble it. Oh, no, assemble. There we go. Okay, so remember the first, oh, I have to initialize x1 and x2 first. Actually, I probably don't, but I'm going to do it just to be safe here. So x1 is going to get a 1, and x2 is going to get a 2. So that means that that branch should be taken because it's checking to see, it's testing if 1 is less than 2, right, based on the current state of those registers. So it's going to take the branch, boom, it goes to skip. Skip is going to go to reset, so it's going to, boom, go up, and check it out. It wrote register 3. Now, what it wrote in there, you say, what is that number? 4,194,320. 4,194,320. You guys probably can't read that. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,194,320. 4,1 Yeah, so what is that number? That's the address. That's the address of that no-op that came after the jump, right? And you can confirm that if you go over here to settings and you say values displayed in hex. Okay, so in hex you can see it's 400,010 in hex. And if you go over to here, you can see that 400,010 in hex is that no-op instruction, right? To check that. Okay, so then I'm going to add, then I'm going to jump, and that should bring me to the no-op, right? And there it is. See? So you can trace through, the sequence. Right? Any questions about that? So the point of that is, the point I'm trying to make is that branches are conditional, jumps are unconditional, but in RISC-V, as opposed to MIPS, all the jumps link. Now you can link them to X0, register 0, which just dumps the link address into a black hole, register 0. But they all link. The hardware will link all the jumps, unlike our old MIPS. You guys with me? Okay. All right. Let's see, where are we at here? So that's branch and jumps. One of the annoying things, I like to bring up the annoying things about assembly language programming. So a lot of times, you really just want to compare to a constant. You want to say, is this value less than 0, or is this value less than 100? What you really want to do is stick an immediate in the branch. There's so many times you want to do that, but you can't, because the branch instructions are already have immediates in them that represent the branch target address. Right? So the only way to compare to a constant value is to add another instruction and reserve another register. So in this case, if I want to check to see if x1 is less than 0, I have to put 0 in x2 and compare to x2. Well, actually, I could have just put x0 there. That was a bad example. Hold on. That's a bad example because there's already a register that always has 0. Let me fix that. Let's say that was 10, right? There we go. That's a better example. Thank you. All right, so yeah, 10, if I want to compare to 10, I got to put 10 in a register, right? Okay. Okay, and then load store. So I already talked about this a little bit. I'll just go through this one more time. So load store uses this base offset, right? So there's a base register that defines the address that you want to load from. In high-level programming languages, this is just called a dereferencing operation, meaning you have a pointer and you want to load the contents of that pointer, right? And then there's a fixed offset, which is an immediate, right? Unfortunately, that doesn't work very well if you have a variable offset, like an array index, right? So in order to implement array indexing, you have to do these addressing calculations. You have to add numbers to the base address, and right, you have to do additional calculations to calculate the new address of the array element that you want to access. Okay, so here's an example of that. So I have this array called foo, and I have it declared as an integer array, and I have I, which is live in x1, and the address of foo is live in x2. So how do I access foo of I? I just want to read foo of I. That's it. It's going to take at least 3 instructions here because I'm going to have to multiply x1, which is I, by 4 because integers are 4 bytes. Okay? So but the problem is that there's no multiply immediate instruction. So instead, I use the shift left logical immediate instruction, which shifting left by 2 multiplies it by 2 to the second power, which is 4, right? So I'll do a shift on that guy, put the result into x3. So I'll leave x1 alone. I'll leave I alone because I might be used for loop control. I'll multiply that by 4, put the result into x3. Then I have to add that to x2. Why? Because x2 is the base address of the foo array. So I have to calculate this effective address, which is the starting point of the array, plus the offset, which is the I times the size of the element, right, which is 4. Right? So I got to say I times 4, add it to the base address of foo, and then I can use x3 as the base address, right? Now you might say, well, that's a lot. I mean, why? It's a lot of instructions to just access an element of the array, but that's how you have to do it. Also, you might notice that the offset here is 0, which kind of makes it looks like the offset's kind of a waste, right? Because the offset's almost always 0, which is true except when you access the stack. Usually they use offsets for stack accesses. Okay, so right, so I have an example of that too in RARS. If we go to RISC-V, here we go. So this is a little crazy here. So we've got this, now I've got this thing called, this is a directive called .data, and I declare my array foo as words 4, 5, and 6. So I initialize this array with 3 elements, and then I have .text. You might ask, like, why didn't we have .text before? Because we only need it now because we have a data section, right? If you don't have a data section, then you don't need to define text. And text means code, by the way. I don't know why they call it text. I never understood that, actually. Text is code. Instructions is text. I don't know where that came from. That's weird. But yeah, so I load the address of foo into x2. This ends up becoming a pseudo instruction, by the way, and I'll show you that in a minute. This expands the multiple instructions just to get the address of foo into x2. The address of foo, by the way, is treated like a constant, basically. So it loads that into x2. Then I do a load immediate. I put 2 into x1. This is I haven't talked about load immediate yet, but load immediate just puts an immediate in the register. It's also pseudo instruction. It ends up being an add immediate with register 0. Then I'm going to shift x1, which is my index, as I mentioned, that multiplies it by 4. I'm going to do the add, and then I'm going to load. So all I got to do is put the only register that I haven't initialized in my code. Oh, I have actually x1. Yeah, everything's initialized. We're good. I initialize x2. I initialize x1. Right. So what should happen here? What should happen is I should be loading from foo at index 2, which should be 6, right? Because that's 0, 1, and 2, right? So what should happen is by the time I get to the end of this, it should load 6 into x3, because that's basically what I'm doing is I'm saying foo of I, and I is 2, right? So let me assemble that. Right, so yeah, there's the load immediate, by the way. Notice the load immediate, the load address rather. The load address was expanded to an AUI PC instruction. This is basically just takes part of the program counter, combines it with the immediate, and sticks it in at x2. We're not going to implement that in class. And then it does an add I. It redundantly adds 0 to it, which is kind of a waste, right? Yeah, that is weird. I wonder how it gets away with that. But yeah, anyway, that x2 ends up becoming the address of foo, right? Then it puts I into register 1. It multiplies that by 4. It adds the base address to that offset, and then it loads. So if I go dink, 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 it should put 6 in there. Yep, there it is, 6. Right, so it's shown in hex, but hex and decimal are the same in this case. Okay? All right, so that's loads. I haven't shown a store, but the store is obviously, when you store it in memory. Addressing is handled the same way. All right, and then finally, this is the last set of, the last type, and this is something you haven't seen in 2.12, are these coprocessor instructions. So in our lab, we are actually not going to implement the loads and stores in hardware, in your project, your CPU project. We used to, but it's part of one of the things that we dropped out of this course as we moved into more, added all the conceptual parts of the class. So if we don't have loads and stores, you might be wondering, like, well, I mean, how do you do I/O, right? You guys should have learned in 3.13 that ultimately the way that you get input into the CPU, whether it's from a network adapter or a keyboard or a mouse, is through loads and stores, right? You do loads and stores fundamentally is how you do I/O. It's not just memory that you're interacting with, it's peripherals too. So how are we going to have your CPU communicate with the outside world? We're going to use this CSRRW instruction. So this is a little bit of a hack that we put in. It's a little non-standard. But what's supposed to happen here is the CSRRW instruction actually does an atomic swap. It takes, because first of all, notice there's a destination register, a source register, and an immediate. The immediate is meant to represent the coprocessor address. Okay, so what it does is it takes the coprocessor register at the address and sticks that in the destination, while at the same time, it takes whatever's in the source register, in the general purpose registers, and it puts that in the coprocessor at immediate, right? So it does a swap. It takes something out of the coprocessor and puts something in the coprocessor at the same time, right? In this class, though, we're not even going to do that. We're just going to use this where if you have a certain immediate in there, immediate number, it'll write to the hex displays. We have these hex displays on the board. And if you put another number in, it'll read from the switches, right? So in other words, we're just doing this as a simple I/O, GPIO. And we have a modified version of RARS, as I mentioned, that actually implements this. So if you go over here to RARS, you go into control and status. So these are the regular registers, integer registers, floating point registers, control and status registers. If you go over to control and status, you have these are all the normal RISC-V. Those are cycle counter. That's pretty cool. I never noticed that before. But yeah, there's like time, cycle. I think some of these deal with interrupts or something, right? They're all like special stuff the operating system usually uses, right? But we added our own 4 at the end that are not normally in here. IO0, IO1, IO2, and IO3. And these are at addresses F00, F01, F02, F03. Right? If this sounds confusing, this is all going to be in the lab sheet once we get to the CPU design. I just want to cover this now just so you're aware of this instruction. So essentially, it sounds more complicated than it is. Basically, all it is you just put F00 if you want to access the switches, right? So in this case, we're going to take whatever's in the switches and put it in X2. So in this case, I'll have to pretend like I have some switch values on the FPGA board, like put 56 in there in hex. And then I think if I run this, it should put 56 into X2. And it didn't. Okay. I don't know why it didn't do that. Maybe I screwed that up. Oh, actually it did the opposite. It actually it did it the opposite way. It put okay, sorry, I'm sorry. Scratch that, I had it in reverse. IO0 is the output. This is for the hex display. So notice what it did was, it took this 10008000, which was in register 2, and it put that into IO0, right? However, if I switch the register to FO2, this is the input register. Go away. Right, FO2. And so if I save this, it should do it the opposite way, right? So this will actually write to register 2. There it is. There we go. We wrote to register 2. Okay, you guys with me? So what I'm trying to say is, let me clarify this. So normally, if you read the RISC spec, anytime you run that instruction, it writes to the destination register and the coprocessor register, because it does that swap I was talking about. But in this class, we're going to only write to one or the other depending on what address you use. So if it's the input, it'll read from it. If it's the output, it'll write to it, just depending on what number you put in for the immediate, okay? All right, so, but we'll revisit that once we get to the CPU. And that finishes, I think, all our instructions that we want to cover. So here's a summary of those. So we have the following categories. We have some R-type number crunching stuff, I-type number crunching stuff, branch and jump, which are very similar, except branch is conditional and jump writes a link register. Load and store, which is very commonly used in code, but we won't have it in our hardware, the CPU that we design, and the coprocessor instructions, which we kind of hacked so you can do FPGA I/O. Okay, any questions? All right. Oh, one other thing too, console I/O. So you need to be able to do console I/O just for lab 1. because we don't have an FPGA board to get data in and out of your program. So the way this works, and you might remember this from 212. You should have did this in 212 too with Mars. Real simple. You basically you use the system call instruction. In RISC, it's not called, in RISC-V though, it's not called system call, it's called eCall. That's one of the minimal changes they made not to get sued by MIPS. So system call and eCall is the same thing. Basically, if you go into the RARS help, if you go to help and you go into syscalls, it lists them all here for you and tells you exactly how to use them. So for example, if you want to print an integer, you have to use syscall 1. The way you specify syscall 1 is you put a 1 into register A7, right? So A7, this is why I said that you're going to, sometimes you have to mix the X registers with the symbolic register numbers. This is an example of that. So A7 is where the system call is going to look for the system call number, right? So you're going to put the number in there. That tells it what to do. In this case, number 1, print an integer. The value you want to print goes into A0, but A0 is the argument. Yes?
If you use the corresponding X register, will it also work?
Yeah, it'll work too. Yeah, exactly. Yeah, it still will work. And then you call eCall. Make sense? Now, some of these system calls are outputs and some of them are inputs. If it's an output, then you put the number you want to output into A0. If it's an input one, like where you're getting text that the user types in, then the input comes into A0, right? But basically, A7 is the number of the system call, and A0 is the argument, which could go in either direction, right? So if you want to do something like print a message, in this case, I'm going to run the print string one, enter a number, right? That's my prompt. Notice it's in the data section as an ASCII Z, it's string. Then I'm going to put 4 into A7, that's the print string, sorry. I'm going to put the address of prompt into A0, and then I'm going to run the eCall, and then it's just going to print enter a number, right? And then, question?
Yeah, so if we're running this on bare metal, how will the system calls?
So the way this will work is in lab 1, we're going to write code that we will eventually run on your lab CPU. But when we do that, we'll be taking this part out, right, and replacing it with the CSRRW instruction that I just talked about earlier, right? So this is the intent here is that when you're running this in test mode in RARS, you got to use this. When you run it on your hardware CPU, we're going to do the switches and the hex displays. So it'll be tangible, actual IOs, right, in that case. Did you have a question? Yep. Okay, so yeah, but all that's described in the help file for RARS. Okay, so I'm going to speed up a little bit. I'm running out of time here. Okay, so this is a summary of all the instructions that we're going to implement. This is really meant for you to refer to later, but these will also be listed in the lab sheet. There'll be a lab sheet that describes exactly what you have to put in. But these are all the instructions, and there are, I forget how many of them. The only ones listed here that we're not doing are the loads and stores, right? So these are not in the core CPU. The other ones are. Okay, any questions about that? Okay, so now I'm going to switch topics, talk about stuff you need for lab 1. Okay, so this is about fixed point. So how do you convert a binary number to decimal? Hopefully you guys remember this from 211, right? The way you do that is you take each bit and you multiply it by 2 to the power of whatever bit number it is, right, or the significance. Right? So in this case, bit 0 is the rightmost bit, right? So you're going from right to left, right? So bit 0 times 2 to the 0th, bit 1 times 2 to the first, bit 2 times 2 to the second, right? So for example, if you have this, which is a 7-bit number, I don't know why I'm doing 7 bits. I picked a non-standard width. But this is a 7-bit number, so the bits are labeled from 0 to 6 from right to left. And if it's 1010011, then in this case, I'll go from left to right. So I'll say 1 times 2 to the 6th plus 0 times 2 to the 5th plus 1 times 2 to the 4th, right? You could go from right to left too, but I usually convert these from left to right. So the significance, the exponents are decreasing, right? You guys with me? You'll remember this, right? Okay. All right, so this number is 83, essentially, right? Assuming it's an unsigned number. If it was a signed number, then it would be a negative number because that first bit would be the signed bit, right? But as an unsigned number, it's 83 if I did the conversion right. I think I did it right. Okay, so the maximum value then as an unsigned number is if you just put all ones in there, right? In which case, the way you can figure this out is, oh man, did I screw that up? Sorry. There's a typo there. Let me fix that. This should be bit 6. There we go. Sorry. Yes. Okay, sorry. Bit 6, this is unsigned, so it's not a signed bit here. Bit 6, bit 5, bit 4, bit 3, and so forth. So if it's a 7-bit, why is it 7? Because it's 6 down to 0, right? So you have to include 0. So it's 7 bits. The maximum number is 2 to the 7th power minus 1 is 127, and that's the highest magnitude number you can put in. The lowest is 0, so the range is 0 to 127, right? If this were a signed number, on the other hand, well, then the most negative number would be negative 64. It's when you have just a 1 in the signed bit and zeros everywhere else. You end up getting negative 64, and the largest positive number would be 63. So you get the same 128 possible unique values. You just get different ranges depending if it's signed or unsigned, right? Okay, so hopefully you guys all remember that. Oh, and also the increment is 1, right? So the unit in the last place, which is the least significant bit, is 1. So you can only get within 1 of any value, right? Okay, but what if the bit numbers were changed? What if they were numbered differently? Instead of 6, bit 6 down to bit 0 for 7 bits. What if instead it was bit 4, bit 3, bit 2, bit 1, bit 0, and then bit negative 1 and bit negative 2? What if we did it that way instead? What if we just basically relabeled the significance of each one of the bit positions, right? If you did that, then essentially what you're doing is you're scaling the number by 2 to the negative 2nd power, or 1/4, right? So that way, if you put the same bits in here, but you assign these levels of significance differently, then instead of 83, it's actually going to be 83 over 4. This is actually 20.75. You guys with me? Now, you may say, why is that? Why did you just divide by 4? Well, that's because this guy carries a weight of 2 to the negative 1, right? So this is halves, and this is quarters. So this is quarters, halves, and zeros, ones, right? Makes sense? So that's the idea behind fixed point, is that you just assume that there's a scaling factor that's implicit. It's not explicit. It's not something that you build in the hardware. It's something that you just imagine as a programmer, right? You just assign this different format to the number. So the other way to think of this is you split the thing into 2 parts. There's a whole number part and the fractional part, right? Now you can change how many whole bits there are. You can change how many fractional bits. You can even make the least significant whole bit non-zero, right? So instead of being 4s here, this could be 2s, right? This could be a significance of 1, right? It's up to you. So one way to represent this is an mn number, where m is the total number of bits and n is the number of fractional bits. So this is a 7-2, meaning 7 total, 2 fractional. Now, some people, that's not a standard way to do it, by the way. Some people will say 5.2, right? Why? 5 whole bits, 2 fractional bits. So sometimes you'll see 5.2, other times you'll see 7,2, meaning be careful that you're understanding how they're representing these things. But the point is that essentially you just have a number of fractional bits, and that's the scaling factor, basically, right? So in this case, the increment is 0.25, obviously, because it's 1/4, right? That's your unit in the last place. Okay, so the range of numbers then changes. The range is now 0 as an unsigned number. It starts at 0, and it goes to 2 to the m divided by 2 to the n minus 2 to the n minus 1. Right? 2 to the n. I screwed that up, didn't I? Yeah, that's a typo. Sorry. That is a typo. 2 to the n, 2 to the minus n. Sorry. Yes. Sorry. Minus n. Yeah, so the idea, let me explain that. Let me explain how that works. So remember before, the range was 2 to the n minus 1, right? The reason it was minus 1 is 1 was the least, the ULP, the unit in the last place. In this case, the unit in the last place has a significance of 2 to the negative 2, right? So that's where this should be 2 to the negative 2. There's 2 fractional bits, right? So 2 to the negative n is the increment, right? It's how close you can get to the number you want to represent. You guys with me? Some people call it accuracy, right? It's basically it's your resolution, how close you can get. Okay? Makes sense? And by the way, 2 to the m divided by 2 to the n is equivalent to saying 2 to the m minus n, right? So in this case, it's basically 7 minus 2, which is 5, right? So that's 2 to the 5th minus a quarter. You guys with me? Okay. Yeah, sorry for that typo. And then there's the signed one and the typos in there too, but I'm going to blow through that real quick because I'm running out of time here. Okay, so I'll revisit that in the next lecture. Okay, so in general then, fixed point is where you just assume that there is a decimal point somewhere other than to the right of the least significant bit, right? You just put the decimal point, and obviously it's not really a decimal point, it's really a radix point because this is binary, not decimal, but most people think of it as a decimal point. That's the dot in the number, right? So normally your decimal point is implied to be here, but you can position it anywhere you want. So for example, this is a 6-bit number with 3 fractional bits, which means whatever binary value is in here is scaled to the 2 to the negative 3rd, so it's divided by 8, right? So you take this, so this is a 6-bit integer is 45, but this is also 45, but it's 45 over 8, essentially, which is 5 and 5/8, right? And then this is same thing, except this is 45 divided by 16 because this is in terms of 16ths, right? Because there's 4 fractional bits. You guys with me? Okay. Okay. Yeah. And then the problem, though, that you have to, the nice thing about this is that using this fixed point format, you can treat these as integers for the purpose of the hardware. You don't need special hardware to do fixed point, right? However, you need extra software support for it because if you remember from grade school, if you have 2 numbers, like let's say this number has 4 fractional digits, positions, bits, 4 fractional bits, and you multiply it with another number that has 4 fractional bits, then the product is going to have 8 fractional bits. Just let's say it works the same way with decimal, right? Because if I multiply 1.5 times 1.5, I get like 2.25, right? 1.5 has 1 fractional decimal position, but if I square it, I get 2.25 as 2 fractional positions, right? Same thing happens with binary, right? So the problem is that after you multiply numbers in fixed point, you usually have to then do a shift operation to round them down to get them back into the original format. This format had 4 fractional digits. When I multiplied it together, I got 8 fractional digits, in which case if I need to get it back into 4, I'm going to have to do a shift, right? Does it make sense? You guys with me? So you often have to, basically it's called renormalizing the data after you multiply it, right? Okay, so, right, I already talked about that. So yeah, so here's one thing you could potentially do. You may have a number that has 32 zero fractional bits, right? And then you can multiply it by another number that's all fractional bits, right? In which case the result will have will have 64 bits in total, but the high 32s are going to be the whole number, right? And the low 32 bits will be the fractional number, right? It just worked out that way because you did 32, 0 multiplied by 32, 32, right? 32 is 0 fractional bits, multiply 32 bits with 32 fractional bits. So you ended up with this nice, nice kind of, it worked out nicely, but it may not always work out nicely. You may, for instance, have, and this is what we're going to do in lab 1, you may have a 32-bit number with 18 whole bits and 14 fractional bits, right? If you multiply those two guys together, if they both have that same format, right? So in this case, they both, like in the previous example, that two different formats were multiplied. In this example, two values of the same format are multiplied, but they have sort of weird numbers, right? 18 and 14, right? If you do that, you end up with a 64-bit result. So you have a high register, which I mentioned earlier, you recover that high register using the mul-h instruction, right? And then you have a low register, which is recovered with the mul instruction. So two instructions, you have to multiply twice to get all 64 bits. But the problem is that that 64-bit result now has 28 fractional bits. Why? Because it's 14 plus 14. The number of whole bits is actually 36 whole bits, right? Now, what's the problem with that? The problem is if I need to get it down to this format again, what do I have to do? I have to shift by 14 bits to the right, round it down to the nearest 2 to the negative 14th power, right? However, you have to shift the whole 64-bit number together as one value. And there's no direct way to do that. Like, in other words, you have to take a register pair and shift the register pair as opposed to just shifting one register, right? So how do you do that? You have to do this thing, it's kind of neat. You have to basically take the low register and shift it 14 bits to the right. Okay, so that part's easy. When you do that, you're going to end up with 18 bits left over. Remember how shifts work, right? If I shift 14 bits to the right, I'm going to shift in 14 bits on the left-hand side, right? And then 32 minus 14 bits is what's left over. The bits that were retained is 18 bits. They'll just be shifted over to the right. You guys with me? Okay, so if I take the original low register, put it 14 bits to the right, I end up with 14 zeros concatenated with 18 bits that were previously on the left-hand side of the register, right? So that part is, I think, is pretty straightforward because your whole goal is to shift 14 bits. The confusing part happens on the high part. The high part, your goal is to get what were originally the 14 bits on its right-hand side. You need to get those into the left-hand side of the final value, right? So the way you do that is you take the high register, shift it 18 bits to the left. What that's going to do is it's going to put 18 zeros in on the right-hand side, and it's going to, sorry, over here, I pointed the wrong thing. It's going to put 18 bits on the right-hand side, all zeros, and 14 bits that were originally on the right-hand side are now moved to the left, okay? Then you smash those two things together. You do a bitwise OR instruction, which merges them together. So basically what you end up with is the high 14 bits, you end up with the high 18 bits. Yes, sorry, the high 18 bits from the original low register end up in the low 18 bits, right? And the low 14 bits in the high register end up in the high 14 bits of the new register. You see what I'm saying here? So basically the idea is, what you're doing is you're taking some of the bits from the high register and you're having to shift them across the boundary between the two registers, right? You're taking some of the bits that were in high and you're trying to get them down into the low. But the way you want to shift them to the right, right? So you're taking stuff that was here, right? You move this down and then you put it into the high bits of the new register. Does it make sense? So what's happening here is this is allowing you to square a value that's in 32 3214, right, format. You're squaring that, and then you're renormalizing it so it goes back into a 3214. You know, you round down, basically. You're rounding down, right? Now, why are we doing that? Because we want to create a numerical method that estimates the square root of a number. We're going to build a calculator on the FPGA. And so basically we're going to use a binary search, and the binary search is going to repeatedly square a number in order to try to converge on the square root of an input value, right? But we want to use this 3214 format. The reason why we're using that particular format is because there are 18 switches on the FPGA board. So we have 18 switches. We're going to treat those 18 switches as the whole bits, right? So in other words, on the FPGA board, you're going to put an integer in, and then it's going to take the square root, which will give you a fractional number. But we're going to still, you know, you're more than likely going to get a fractional number when you make the calculate the square root, and then we're going to put that fractional number on the hex displays. That makes sense? That's the goal of Lab 1, but unfortunately, did not get far enough to finish talking about Lab 1, so I'll have to finish that in the lab on Wednesday and Friday. Okay? So we'll see you in lab. If you're interested in what the lab requirements are, check Blackboard. Thank you.